Okay, well, thank you guys very much. That was a good fire drill. We're all safe. Yay. Okay. So we don't have a whole lot left to do. I think we have one problem overall. Then I'll just give you the rest of the time to go ahead and work on your assignment. Remember, the assignment's due on Tuesday, but I would like to go ahead and take the opportunity to look at those problems together, because probability is typically the unit students have the most difficulty with, especially when we start getting into the next lesson. But the only thing, remember, Monday is your what? It's going to be your test, so it's going to cover these past three lessons where we introduced sets, intersection, union, complements, Venn diagrams. We moved into truth tables and all that good stuff, implication and equivalence. So if you have any questions, definitely let me know. You can come on in Monday morning. I'd help you out. So let's see here. I believe. Okay, we did this one where the coin is being tossed 3 times. Okay, so we're to this one right here. Okay, so we're given the probability of these values here. Let me go ahead and get my notes very quickly. Okay, so if the probability of A is equal to 0.6, the probability of event B occurring is 0.3, and the probability of, what does that mean? That upside down U. The intersection, so the probability of A and B occurring is going to be 0.2. Okay, we'll find the probability of A or B occurring. Well, can anybody tell me just right at the top, is this a situation where A and B are mutually exclusive, or are they not mutually exclusive? What did mutually exclusive mean? That's exactly right. Okay, Emma's right. That means they don't have an intersection. They don't have events that could occur at the same time. Now, we have no idea what A represents. We don't know what B represents. But because they tell me we have a probability of the intersection of the two, that means they are not mutually exclusive. Not mutually, that's a horrible L, exclusive. Okay, and I've already got a Venn diagram set up down here where we'll go ahead and fill it out in just a minute, but I want to go ahead and work these problems both ways. I want to go ahead and apply the ideas that we've recently learned from sets that was at the beginning of this lesson, and I want to show you how we could do this within the Venn diagram. So the probability of A union B, so if I go all the way back to the beginning of this set of notes, okay, if A and B are both subsets of the universe, if they are not mutually exclusive, then this is the formula that I want to use, okay, for the union. So I want the probability of A plus the probability of B, but then I want to subtract off the probability of the intersection. So let's see here. I'm going to come on back. Let me go ahead and write this formula down. So this is equal to the probability of event A occurring plus the probability of event B occurring minus the probability of the intersection of both events occurring. Okay, now we're choosing this one specifically because they are not mutually exclusive. If they were mutually exclusive, if there was no intersection, then we wouldn't need to subtract the intersection. It would just be the probability of A plus the probability of B. Well, let's see. What was the probability of A again? Okay, 0.6 plus the probability of B, 0.3 minus the probability of the intersection. Okay, so 0.6 plus 0.3 minus 0.2. 0.7. Okay, so there is a 0.7 probability of A or B occurring. So we're saying 70%. Okay, well, take a look at B. Probability of B, and it has that little tick mark. What does that mean? The complement. Okay, so related back to what we've talked about with the complements, we're talking about everything in the universe but not contained in that set, right? And then we had some other ideas. What if I take set B and I combine it with B's complement? That's going to give me what? Does anybody remember? Like, let's say we have A, and then we have the complement of A. So if I go ahead and take A plus A complement, that gives me something in particular. What do we call the rectangle of the diagrams we've read? The universe. Okay. Remember, because they're going to make up different parts of the universe. By definition, A complement is everything inside the universe, but still outside of that set A. So the same idea is going to apply here. But our universe, all of our probability, remember again from the front page, is everything between 0 and 1, where 1 represents a 100% chance of that event occurring. So the probability of B's complement, I'm just going to go ahead and take 1 and subtract off the probability of event B. Does that make sense? Okay. And in this case, we know the probability of B is 0.3. So 1 minus 0.3 will give me 0.7. Okay. Now, you can actually go ahead and work these not only by knowing these formulas, but you can also work it on a Venn diagram. I mean, let's go ahead and set it up. You'll notice I've already got two overlapping sets here. So let's say this is event A, this is event B. We got the universe. Okay. Well, what's the intersection of the two? We know this is going to be 0.2 right here in the middle. But what should I put here in only event A? What's the probability of A occurring? What was that? 0.6. But because of the intersection, we've already accounted for 0.2 of that. So only 0.4 should be written strictly for A. Would B just be 0? Okay. Well, not quite, because the probability of B occurring is 0.3, but again, the intersection, I've already got 0.2. So what would go here in strictly B? Point what? 0.1. There we go. Now, I'm missing something. Remember, what's the universe in this case? 1. Okay, 100%. See, I've only accounted for 0.4 plus 0.2 plus 0.1, so 0.7. So somewhere outside these sets, but still inside the rectangle, I need to go ahead and put that 0.3. So there's a 0.3 probability of neither of those occurring. Is everybody okay with that? But go ahead and take a look. I mean, if you think about how we've shaded these Venn diagrams in the past, the probability of A or B. Remember, the union is a combination of the two. Okay, remember I called it a marriage. So I'm going to take everything in A and everything in B. And you'll notice 0.4 plus 0.2 plus 0.1 does give me what? 0.7. Okay. Let's go ahead and compare this to part B. The probability of B complement. Well, remember, that's everything outside of set B, right? So I'm going to go ahead and take everything outside of B. Okay. Well, what am I adding up outside? What is outside of B? Well, we're still contained in the universe, but what decimals are in the universe but outside of B? Okay, we've got 0.7, the 0.4 plus the 0.3. And see, that's exactly what we got here. Okay, so there are several different ways you could approach these. So what I'd like you to do, try C. Now, whether you want to go ahead and come up with the written way of doing it, or if you feel better using the Venn diagram, completely your choice. Let me go ahead and give you a few seconds on that. Let me erase this. There we go. So the probability of A and B complements intersection. The probability of A and B complements intersection. Okay. Now show of hands, how many people think they have the answer? Okay, Sarah Beth, what do you think? It is 0.4. That is exactly right. Okay. If I'm looking for the intersection of everything outside of B and A, well, I don't want anything in B. It's going to be in the universe, but the only thing I can combine it with A would be this crescent region right here. So it is 0.4. If you were to go ahead and write it out, and you didn't want to go ahead and look at the Venn diagram, I would have done it like this. The probability of event A occurring minus the probability of A intersecting B. And see, that's exactly what we end up with. The probability of A 0.6 minus the intersection 0.2. And it still gives you the 0.4. Okay. How many people got that one right? Fantastic. Fantastic. Okay. All right. So what's the probability that we loved this lesson? Well, pretty low. But we probably still liked it. Okay. All right. So you've got your assignment. Why don't we go ahead and try one problem together? Is there one problem that you're looking at and you're thinking, I just don't know what to do? Okay. Remember, this will be due at the end of the day on Tuesday, so we'll come in, hopefully not have a whole lot of questions on the assignment, or excuse me, on the test, and then we'll spend the majority of our time just talking about probability. Okay. And if we do have questions on the test, then we'll just go ahead and move it a day ahead, but I'll let you know when we get there. All right, so what are we thinking? Two looks like a lot of work. Okay. What number did you say? 8. You're on the wrong homework assignment, sir. This one only goes to 6 questions. It looks like this. Okay. Alrighty. All right, so where are we going to start? Want to do 4? Okay. Let's take a look. All right, so number 4. Okay, so illustrate on a tree diagram the sample space for A, simultaneously tossing a 5-cent and a 10-cent coin. Okay, so remember, a tree diagram is just where you use branches to show every possible outcome for certain events. We did them yesterday with coins, and we did them with, having boys and girls. So it really doesn't matter how you go ahead and start. What would you like to flip first, the 5-cent or the 10-cent coin? 5-cent, because we're going to go ahead and make sure to label our tree diagram. So I'm just going to write over this so I don't have to keep going back and forth. So A, let's say the first part of the tree diagram right here represents my tossing the 5-cent coin, the nickel. All right. Well, if I go ahead and toss that, well, what are the 2 possible outcomes? You can either have heads or you can have tails. So when I go ahead and continue the tree diagram, that second toss here is going to represent the 10-cent coin, the dime. Okay. So let's say on the 5-cent coin, the nickel, I toss a heads. Well, then I go ahead and toss a dime after that. Again, there are 2 possibilities, heads or tails. Or if I toss the tails first, there's a heads and tails. So there are 4 possible outcomes. And that's what you want to do on 4. Okay. So let's try B. Tossing a coin and twirling an equilateral triangular spinner labeled ABC. Okay. Now again, whichever one you're deciding to go with first determines how your tree diagram is going to begin. Do we want to start with the coin or this spinner? Let's start with the spinner. Okay. Well, let's say I go ahead and spin it. How many possible outcomes are there? There are 3, A, B, or C, right? So for B, I'm going to go ahead and start with a tree that has 3 branches. Because if I spin that first, I could either end up with an A, a B, or a C. Now, regardless of which one of these happens, after the spinner lands on one of those, I'm going to do what? I'm going to flip the coin. So if the spinner comes up A first and I flip the coin, there's the possibility of getting a heads or a tails. If it comes up B, I have the possibility of heads or tails. If it comes up C, I have the possibility of heads or tails. So there's 6 total outcomes for this scenario. Okay. Is this making more sense? So see, you could have gone from 2, the heads or tails, and then had 3 branches coming off of each of those for A, B, and C. Would have looked like a different tree diagram, but has all the exact same outcomes. Okay. Hey.
For shape diagrams, no matter like if we have to do it to the side or can we just do it down?
Actually, that's a good question. I don't see any problem with going down. I've always gone from left to right. I just have it, but no, it wouldn't affect anything at all. Okay. All right. What else? Do we want to go ahead and do C or D, or we think we're okay with that? We'll be okay.
I don't know.
Okay. All right. Very good. Anything else? Okay. If anybody changes your mind, let me know. I've got 57, so we still have about 11 or 12 minutes left. A decent amount of time. You could probably go ahead and get at least halfway through your assignment if you haven't already started it. Okay, so I'll pass back if any papers if I have some, and then I'll be around.